Hello, everyone. I hope you're all doing well and enjoying summertime. My name is Mattia Rüfenacht, and today I do have the pleasure to sit down and talk with Andre. You may ask yourself, why yet another podcast host? Let me share the backstory. When I was recently sitting in the train listening to the latest episode of this podcast here, I was thinking to myself, why is it that we actually never had someone from the machine learning team on? And this despite the fact that Parashift is an AI company through and through. When I then mentioned this to Alain, he just said, good point. And a couple of hours later, Andre and I got an email, and here we are. But enough of this preamble, and let's get started with who are you and what is your background?
Hi, I'm Andre. I'm a physicist by training originally, so I have a PhD in space science. Did a couple of years of research in the US, then came back, wanted to go into AI. Had already spent a lot of time, like private free time, into the whole machine learning topic. That was back in 2013 or so. And yeah, I was looking for opportunities in industry because I knew I didn't want to pursue an academic career. And then I got hired at Parashift. I kind of saw the job ad. It sounded interesting. And yeah, I was the first guy doing machine learning at Parashift. And ever since we are here and growing the team one by one on a kind of a semi-yearly basis.
Very cool, very cool. On this point, what actually back in the days got you into the space science topic? What was the triggering point there?
I was interested in physics foremost, and I studied at the University of Bern, and they have kind of a couple of topics that they pursue. One is like space science, one is climate science, theoretical science. And I was somewhat interested in space science. It was not like a childhood dream or anything like this, but it was kind of the most interesting topic that I thought, because it's kind of a good mix between theory, but you could also kind of applied physics in kind of spending time in the lab, so you don't have to always sit at the desk. And it's kind of, you can build instruments and then actually send them to space, which is pretty cool, which I don't think a lot of people can do or have actually the chance of doing. And so yeah, it's just pretty interesting choice to me.
Talking stars, talking planets and whatnot, what then brought you to such a mundane topic as machine learning on documents?
Well, machine learning in specific was interesting to me, as it's kind of a mix between programming, which I did for like this data analysis task. So I'm kind of used to work with data, stare at data, and kind of wrangle it around in the PC, and math. And I think the kind of liberating thing that I think in machine learning is that in physics you're always constrained to laws of nature. Ultimately, there's kind of a judge nature that tells you you're wrong or you're right. Machine learning, you can you do have a little bit more freedom, and then if you produce something that works, it works, and it can already produce value, even though it might not follow the any principled rules of nature. So it's kind of an interesting and liberating kind of thing to me, that doing math in a non that strict approach. I mean, there's people who kind of do fundamental kind of math driven machine learning and like proven theorems of like learning convergence or stuff like that. But here we are more on the applied side, where I think we do enjoy more of that creative freedom.
Yeah, got it. Okay. Before, and probably some of you, at least by now, realize that today is most of the talk all about machine learning. But before we actually dig deeper into the topic, I think it's worth hearing from you and your perspective. What actually is machine learning, deep learning, and AI, and what is it really not?
There is this famous or semi-famous phrase that machine learning is a glorified function approximation. So, to me, that's somewhat true. I mean, you can look at it that it's kind of a super powerful approximator for any type of function that you wanna rebuild. On the other side, it's kind of alchemy, and also has this experimental side that I also mentioned before, where sometimes people only understand after the fact why something is kind of working and why it's working, and maybe one or two papers in academic senses down, they actually get the full grasp of some of the ideas that they were having and understanding why it's actually working, or a different group actually proving something why for example a convolution in these computer vision models are good ideas. And the other side is kind of it's just learning from data. So like that's also kind of a powerful idea. I think that you just provide a machine that kind of tweaks itself by looking at data and tries to kind of regulate itself so that it comes to the right conclusions or decisions that it takes just from looking at data. And this ties it also a little bit to the real world, where if you have like real data, this kind of has a big influence of what your actual model is doing. So you can have the similar kind of model, but depending on what you train it on and what the actual goal is, how you formulate the problem a little bit, can lead to completely different models. So that's kind of the fascinating thing to me.
Okay. You mentioned convolution. I assume many of you don't know what a convolution is. Can you share a couple of words about that and maybe shine some light or on this method?
I mean, on a higher level, you can think of it's basically just a rule or a method, you could say, that kind of defines a way on how you want to combine several values into one. So you can say an easy version of a convolution would be just building an average. So you can imagine I have a convolution over a certain space of data. Let's say an image. So your data is actually the values of the pixels, and you could just say, okay, the simplest convolution I can think of is an average. So I go over a window of 5 by 5 pixels, so horizontally and vertically, and then I just compute the average, and this is then the new value, kind of a aggregated value. Then you can add some weights to it, so you can say, okay, actually the pixels in the corners are more important, and by adapting this kind of algorithm on how you aggregate this data and how you kind of combine it, you can get different properties. You can derive at something like edge detection or some kind of encodings for like discovering specific textures in, for example, images of animals. You could train something that a convolution kind of enhances the difference between a fur and kind of what's the fish skin? I don't know, something wet or something dry. And so by applying this, you can kind of get a different features of your data. And actually the fun thing is that back in the day, people actually did it. So there's some kind of pre computer convolutions in programs like Photoshop or any type of image processing software that actually does this, but this is usually kind of human created rules. But the cool thing in machine learning is that the machine will figure out itself to actually apply those rules, and then trying to figure out some meaningful information from your data by just training.
Okay, cool. Thank you. So, I mean, Parashift is all about document processing. I know document processing, whatever this term means, has been here for quite some time. And now this somewhat new or not really new technology called machine learning, but also deep learning, arrived. And what is it really all about, talking document processing, and how do we at Parashift instrumentalize these technologies?
Yeah, there's a lot of things you can do on documents with machine learning. So it's like obvious things. If we stay in the realm of computer vision, we can kind of do enhancement of image quality. For example, you can fix some artifacts that you get, for example, from JPEGs. So if you take a cell phone image of your receipt or any type of document, if you zoom in, you kind of know these artifacts from JPEG around the fonts, and then you can get rid of those. You can kind of sharpen the document, but you can also cut out, kind of do a segmentation problem where you find certain parts of the image only contain a document. We do classification, so kind of distinguishing what type of document is it actually. Is it an invoice? Is it a lease contract? All these things. And then finally we have you get things like layout analysis, where you can kind of figure out how a document is kind of built up. You could do sentiment analysis, which we don't do at Parashift. But for this, you could also figure out kind of different parts of the document. What does this mean if you have kind of a support ticket from a customer? And in the end, we do information extraction on documents. That means we try to actually extract useful information from a document and put it into kind of a structured data set. And this could be anything from like, where is positions of logos? Did people put their signature in the right place in a contract? Did all of the parties sign? Do we find a table, or give me a specific date from when this document was created? So there's a lot of things, and yeah, it's actually it's much more exciting, I think, of a topic than one would think. So documents have a lot to offer in terms of complexity. You can mix the different modalities between the textual information and the visual information, which is pretty interesting, and which a lot of the research is now going to. But also, yeah, the raw variety of documents is also pretty interesting. So people are pretty creative in how they produce documents and what they put into documents in what specific format. And yeah, it really has to offer quite a lot of different angles of approach. So it's actually super interesting. I enjoyed it a lot.
I got to realize this as well. Now, it's also the case that using machine learning for reading data and doing whatnot with documents is nothing that just Parashift does. How is machine learning at Parashift different? What do we do differently?
Well, the main differentiator is, I think, the swarm learning that we also have on our website pretty prominently, which is at some point we decided it's kind of probably not the best idea in terms of generality, because in the end we want to be kind of the platform that you can throw any document at. So not only invoices, because there's a lot of people doing invoices or specific niche focus target documents that we have, but we want to actually be super generic. And so the way how we think we get there is by trying to share learnings as much as possible across different document types, across different tenants, and across different use cases even. So we try to really have the swarm learning where if you decide to reuse specific fields or field sets, like let's say something like an address that you want to extract, and you use one of these pre-built models, you actually also contribute to improving this thing. And so we don't have these like specialized models that every customer has its own specific niche model, but we try to reuse this as much as possible.
Cool. So I know this comes with quite a bit of complexity. How does this impose, or what challenges does this impose on the operation side of things when we're talking about these machine learning models?
Yeah, so for one, people can decide if they do want to use these kind of pre-canned models and kind of improve them, or if they for some reason think they want to start from scratch, they can also do that. So one difficulty is to have these different use cases all tackled, to find kind of as low number of models as possible that work well for all these different use cases. So it could work on kind of very structured documents like an invoice, but also on something like a letter. So this is kind of an implication on the models itself, so that it should work in these, they call it, or we call it in the community, it's called visually rich documents that actually have a structure, and you as a human, you can also kind of squint your eyes a little bit and still figure out, okay, this is probably kind of a total amount, and this is kind of the title, because it's kind of visually somehow has information, and completely unstructured or very low structured documents. So that's one problem. And the other thing is we have a lot of models. So if people want to decide to have their own models, we let them do this, and so every customer can actually train as many models as they want, and this leads to, I think we have over 1,000 different models in production at the moment. So they need to be updated, they need to be monitored, benchmarked, and trained. So we have, I think at any point in time, we have at least 50 different models training. So we use up quite a lot of Google's infrastructure at the moment. And that's, so it's being as generic as we want, and kind of having this sharing concept in place makes it a bit challenging on the whole architectural side of things. That's true.
Yeah. Okay. So there's this saying in machine learning, and you already beforehand somewhat implicitly mentioned this: garbage in, garbage out. Now, the issue with this is that compared to classical or traditional software engineering, machine learning systems do not per se break when there's a bug. So you cannot simply generate a bug report and then debug your system. Instead, your system, your AI or machine learning system, might contain wrongly annotated data that influences the model's performance, but does not break it. Is it fair to say that in at least many cases, having more accurate training data would increase performance disproportionately compared to more powerful algorithms?
Yes, I mean that's a common phrase in ML, that good data beats good algorithms. So yeah, that's also something we've actually experienced. We had we actually don't. We have a distinction at Parashift between bugs and oddities, where for machine learning terms, when a model doesn't perform as it should, but you look at what it actually did produce and you think, oh, that seems weird, then we kind of don't do a bug ticket, but we have an oddity ticket, and so people try to investigate this. Which is insightful many times. Sometimes it's also a bug that, as you said, the model doesn't break; it just produces maybe garbage results or results that are unexpected. And now I forgot what I wanted to say. But for one actual use case, we tried to improve the model here and there, and we introduced like more clever tricks that we could build in, some pre-processing steps, and we tweaked out a little bit of performance here and there. But in the end, we just threw a little bit more data at it, took a good look at the already annotated data, saw some inconsistencies, not necessarily stuff that is wrongly annotated, but just from a machine learning side inconsistently. And that actually had by far the biggest impact. So yeah, good quality data is definitely very, very important.
Given that a lot of the solutions or benefit that Parashift provides comes from the swarm, so people from all kinds of regions on this world contribute to this data intelligence, having a clear training ground is super important, or training databases. Are there any interesting or promising approaches to somewhat proactively try to mitigate for the risk of poor training data?
Nothing that we have in place now, but it's actually planned for later in the year that we actively look into this topic and try to find a systematic way on kind of sifting through the data, also getting rid of duplicate data sets that we have at the moment. For example, if a customer at the moment uploads 5 times the same document, we just keep it 5 times, which is also not necessarily the best thing. So yeah, I mean, slicing and dicing the training data and kind of figuring out what performs well also ties into how you measure the quality of your model. So having a really solid kind of benchmarking data set is absolutely important, and we're actually building a new benchmarking set right now. And yeah, there's various ways of ensuring this, and which we want to tackle in the future. But at the moment, this is all planned. So there's a lot of work going into this area.
You mentioned benchmark. Maybe here a silly question: what is to you a hard problem?
A hard problem?
Yeah.
In terms of documents, or
no, generally speaking.
Rocket science.
Whatever you choose, it's up to you.
Well, anything can be a hard problem. It always depends on how good you want to solve it. I mean, if you want to be, you just turn on YouTube or TikTok and you find any mundane task. There's one person that does it to a ridiculously crazy good level. So I think any task could be hard, but in general, and if I pull it to maybe the Parashift vision, of course, documents with complex structures are hard, or also where the use cases are where the actual problem is not well defined. I think that's a lot of times this is a source of making things harder than you think if you don't have actual kind of a real measure. So a benchmark also needs to be good, but for this also kind of what you measure must be clear. So yeah, that's to me a hard problem. So
what then is a somewhat good benchmark when we're talking about documents? You just mentioned you're currently working on this topic. What does qualify, or what means to yourself a good quality benchmark in document processing?
Well, first of all, it should be kind of representative of the real world, or in our case of our customer base, or of the documents of our customer base. It must reflect somewhat the real world data. So one necessity is that if we perform better on the benchmark, we also perform better in real life. So that's kind of the representativeness. And the other thing is it has to be of high quality, as I said. So we really need to trust and double, triple check every annotation so that there's no mistakes. Because if you wanna produce models that perform at kind of the human error rate or better, which means it should perform equally good as a human would do, then you also need training data that is at least as good. Probably you need training data that is much better. So the amount of error in this training data set has to be very low, and in the end it should be kind of large enough that statistically it has some relevance in the real world also, that you can already detect small changes and small gains, because usually initially gains are easy to measure because you just improve by a lot and then it's super clear, but eventually it's kind of unclear if this is just a lucky coincidence with your benchmark set, so that you just overfit it secretly to whatever documents you have. If you only test on 5 or 10 documents, this could easily happen. So yeah, that's what I hope for.
Okay, cool. So I personally realized that there's quite some excitement in the community about self-supervised learning, especially for language models that hit the press quite a bunch of times in recent time. Vision seems to be somewhat different. Can you share a bit more what self-supervised learning is all about and how it can be beneficial specifically for document processing?
Yeah, sure. So the whole deal about self-supervised learning is that it's costly to produce good quality data. So you need, if you want a human annotated data, you need to pay a human, instruct a human. Someone has to sit down and kind of use human resources for this. So this is expensive, even though there's some cheap offers for doing this, but in the end it costs money and or time. So even if you have a lot of money, if you don't have enough people, you cannot just produce as much data as you want. So self-supervised learning is if you find a way of generating labels by yourself, so finding a clever way of taking actually unlabeled data, or maybe just data that has a little bit of annotations, and then find a way on how you can actually produce labels from yourself, so from the document, that you don't need actual humans to do this. So one example is in the language world, you can kind of collect sentences from the internet. You randomly mask a couple of words in there, and you ask the model to reproduce the words. And that's easily doable because you actually knew ahead of time what the word was. You just remove it, and then you can compare it to, and you say, okay, I removed the word house, and it produced the word garage, so it's maybe somewhat good, but if it would produce the word house, it's better. And then you kind of get access to a whole range of data that actually, and labels that no one actually, or no human has to annotate. And in terms of documents, this has been going on for, I think, about 2 years, that people started with these self-supervised or pre-training models, as they're often called, with different tasks also of producing also this masked language or masked token prediction, as they call it, because on an invoice, for example, you don't have natural language. It's usually just kind of a collection of a few keywords and values that don't have any like natural language meaning, like an article number or something like this, which you don't find like proper representations for it, or really meaningful representations of it out of the box. But actually this is a pre-training task that we're looking into. So like masking different parts of the document and trying to give it a label of what this token should be. So kind of predict if there should be a date at this place, or if there should be something like an address at this place probably, or a person name. So that's something we're looking at for these multimodal models. You can try to, so multimodal means you have you take the image information and you take the textual information and maybe an audio information. So these are different modes, so visual, textual, audio, you name it. And one common problem is that they have to kind of somewhat align. So you want to be able that the model is actually not only able to predict that there should be a date at this position, but you should be able on textual level, it should be able to predict a date. But and then on the image a kind of branch of the model, it should also be able to predict, okay, the date was actually in this part of the model. So kind of to align these two modes. And there's a lot of different tasks that people are doing. So every other paper introduces a new self-supervised training task, which is super exciting, because I think this is one of the most promising parts, where if you have clever ideas in this area, I think you can go places. Yeah.
What else besides self-supervised learning excites you that you see in the basic, but also in the applied research space for document processing?
Well, I think it's still. I think the document understanding scene is not at that point. If you look at the NLP kind of side of things, there seems to be like a consensus that the BERT model does a pretty good job of representing text as feature vectors, which is just a bunch of numbers to people not familiar with. So BERT is a model that actually takes text and assigns to each word or subword, let's say word for now, a specific set of numbers that actually capture apparently meaningful information about this word and the context that this word actually appears in. And so whenever you try different NLP tasks or have models that are more complicated or rely on these textual representation, it's usually they fall back to BERT or some kind of version of BERT. In the document space, this point has not been reached yet. So I think finding kind of this base document representation model that then will just kind of run through the scene and we'll just build on top of that. I think that has not happened yet. So I think that's also where a lot of these pre-training tasks lead into. And yeah, that's pretty exciting. And I think that's kind of one of the obvious ways or questions that we need to solve is kind of find a very good representation of not just language, but actually a document.
I somewhat followed some of the activities of your team, and something that you, I think, kickstarted early this year is a venturing into applying graph neural networks to document data. How about graph neural network? What is it? What excites you or fascinates peers within your team about this methodology?
It's one of the hot topics, I think, general in ML. So it has been shown to be pretty powerful technique in all kinds of different areas. So I think in general, this is a hot topic. It's at its core, it's a simple idea to understand, also to visualize, which I think is also one of the challenges in machine learning. If you have like a super complex idea and you cannot sell it to, let's say, investors or customers or communicate to anybody, that makes it obviously much harder in interacting with those ideas or even just getting excited about these ideas. So a graph neural network is a pretty simple idea. You have kind of nodes, which is if you think of a graph, I mean, people maybe have the picture of a social network in their head. So a node would be kind of a person or let's say you and me are two different nodes in a graph, and then there's graphs, there's nodes, and there's edges, and then edges could be connections. So like we have kind of maybe I'm following you or you're following me, so we might have directed edges or not. For example, there might be an unrelated person that is not connected to you or me, but through different friends. And so through these graphs, you kind of try to figure out how information propagates through these graphs, or how what is the actual meaning of these edges or say connections in these graphs, and kind of try to figure out how we can leverage this. And in documents, an obvious representation is to see kind of all the words in a document as nodes, and then you have to find the connections between those words. For example, it's not super obvious in a table, like the connectivity between these different words is more vertically, and in a regular text is more horizontally. So finding these kind of connectivity lists, as they're called, is also pretty interesting.
Okay, cool. Thank you. So before we end this podcast episode here, we're already a little bit north of the time that we agreed. Let me ask a question that I got from Jakub from your team. When do you expect us to surpass human level performance for both the classification and the extraction task?
Okay, when do we? I mean, that depends. I think I did a kind of a high level estimate on how many ground truth examples we need, and then I got a number from like hand wavy, a couple of millions, I think, of documents, which should be enough. And I think, to be honest, people overestimate humans in these repetitive tasks. So whenever you talk to to anybody, they think a human will just sit there and kind of extract data perfectly and will make no mistakes, which is not true. And I think actually in a few of our best performing fields, I think we are probably at the human error rate, because sometimes if I sift through the past examples to try to figure out when a model didn't perform as well, and more often than not I find that it's actually a mistake on the side of the human. And yeah, that on the really good performing models, this already happens. In terms of classification, I think it's more tricky, because there you have these subtle nuances of, I think, a lot of domain knowledge that is hard to capture just by looking at the document and not having kind of an active knowledge of the world these documents or for, say, the industry these documents were produced. So I think in classification we're for sure a few years out, and I'm not sure without getting any of this extra kind of domain knowledge into the model that we can do it.
Okay, cool. So one last question, sorry. What does the roadmap or future hold for you and your team specifically, say in the next 12 to 16 months?
12 to 16 years. Yes,
that's you who said it.
I mean, the thing we're most actively working on is kind of few shot learning and document representation learning. So the goal must be that with only very few or a handful of annotations, that people would already get like very good results out of the product. And whenever I'm a super data driven and number fixated person, but when it comes to I use a handful and pretty good, because it really depends. Like some documents are super easy to do. Like if you have a form, of course you send in 5 times the same form, it must be perfect after the first time, no question. So there actually the error margin is super low. But if you have very complex documents, there might be no chance even with 20 or 30, but we then talk about the hundreds. But so even though, I usually get asked and called out on, you mentioned very good and a handful. What does that mean? I don't know. It really depends. And as I said, this representation learning is super exciting. So we started introducing a couple of new of these pre-training tasks. That is certainly interesting, and a lot of tooling. As we mentioned at the beginning, we also have a big infrastructure, and how we train these models, how we update these models, how can we leverage not only like we call it Swarm 2.0, and not only learning between different fields in the document, but also kind of behind the scenes figure out relations between different fields that maybe people wouldn't expect. An obvious way would be between all the addresses, but you can have very different addresses depending on your document type. So it could be kind of a member list where it's kind of a flat list, but you could have these postal addresses that you have on your mail. So kind of broadening and making a more broad approach on what we can actually learn. I think in the very broadest approach in this document representation learning, where we want to formulate very generic tasks to just get this generic representation of a document that is useful for classification or for extraction. And then the other goal is to really only need a few examples to actually lead to surprisingly good results.
Cool. What a better end would there be to leave it here. Thank you, Andre, for taking the time, and also thanking to you out there. I hope you enjoyed today's session, and look forward to welcoming you eventually again on this podcast here. Thank you.